Alright class, today we are going to talk about the uh, Exergy. So basically in the last class we talked about the Exergy change of a system, and that system was a closed system. So today we are going to talk about topic 8.4 Exergy change. However, the system will be open system or Exergy of a flow system. Flow system, right? So flow system means that another term it would be open system. So let's consider a pipe, right? So in that pipe water is flowing, or the fluid is flowing in this direction, right? So since this pipe diameter has fixed, we can imagine, or we can consider, a piston right here. This is the imaginary piston, right? So imaginary piston along the cross section of the pipe, right? And then that piston will experience some pressure of the fluid, right? So the pressure of the fluid in atmospheric, it will be P. However, when it's the pressure on the piston, actually atmospheric, it is P naught, and however the imaginary piston is experiencing the pressure which is equals to P, right? And then the volume, or the air displaced, atmospheric air displaced volume is V, right? And then this, when this fluid is putting pressure on this piston, it's generating, or it's producing the work which is W S H F W shaft. Okay, so now let me write it here: imaginary piston. Okay, so imaginary piston. So in this case, what would be the W shaft, or what would be the work, right? Work done by this system. So in previous classes we saw that when the closed system, the relationship equals to delta W equals to P dV, right? And when the system is open, then the relationship delta W equals to V dP. So we saw this relationship in previous classes, right? But for Exergy, similarly for Exergy, the relationship for X flow, right, if it is a flow stream, X flow would be that P times V, which is the piston pressure, and this is higher considered to the atmospheric pressure, right, minus P naught times V. So it will become V times P minus P naught, right, which is ultimately this relationship, VdP. Okay, so now we know that X flow, Exergy for flowing stream, and we also in the last class we talked about the Exergy for non-flow stream. That means that closed system, right? So the Exergy of flowing fluid would be flowing fluid would be Exergy of non-flowing fluid. That means that this portion, right, from here to here, non-flowing fluid, non-flowing fluid plus Exergy of flowing fluid, right, flow. So we know that for non-flowing fluid, or non-flowing fluid, the Exergy change equals to internal energy change plus P naught times V minus V naught minus T of S minus S naught plus V square divided by 2 plus Z, right, plus for X flow it will become P minus P naught of V, right? So That's the expression of Exergy for a flowing fluid. So if we simplify it more, then it will become U uh, plus U plus PV minus U naught plus P naught V naught, right, minus T naught of S minus S naught plus V square divided by 2 plus GZ, right? So we know that this relationship here, it's enthalpy, right? So basically it will be H minus H naught minus T of S minus S naught plus V square over 2 plus GZ. So that's the expression of the exergy of a flowing fluid. There is a name of this expression which is called flow exergy. Flow exergy expression, right? So we see that the exergy for a flowing fluid, the expression of exergy for a flowing fluid, right? So the flow now if we express it in terms of there is the flow exergy expression, it can be expressed by psi, right? So that psi is basically H minus H naught minus T of S minus S naught plus V square divided by 2 plus G, right? So this is the flow exergy expression, right? Now if we have exergy change of that fluid stream, and then and it undergoes a process between 1 to 2, then the the flow stream change or exergy change will be expressed by delta psi, which is equals to psi 2 minus psi 1. Basically it will become H2 minus H1 minus T naught of S1 minus S2, actually S2 minus S1, right, plus change in kinetic energy V2 square minus V1 square divided by 2 plus change in potential energy G2 minus G1, right? So that's the expression for exergy change. Now exergy change of a closed system or a fluid stream represents the maximum amount of useful work, and we saw in reversibility and irreversibility section, right? So exergy change of a closed system or a fluid stream, right? That means that open, either closed or open, right? In either cases, the fluid stream represents the useful work. If I ask you guys that, determine the exergy change or determine the useful work of a thermodynamic system that is undergoing from state 1 to 2, then you have to determine the exergy change, which is basically the representation of the useful work, right? So this statement is applicable for work producing device, right? However, if you have like work consuming device, then this closed system, the fluid stream, represent the useful work. Actually it represents the maximum, okay, let me write it, maximum useful work. When the exergy change represents the minimum useful work, then it becomes the work consuming device, right? So, and of course it has to go through for reversible work, right? That means that this the system changes from state 1 when the system undergoes from state 1 to 2, right, in a specified environment. In a specified environment, and represents the reversible work, which is W, right? So that's the relationship between the exergy change between two specified state, right? So now let's take a look exergy change due to the heat, work or mass, right? So what is the expression? So topic 8.5, exergy transfer by heat, work and mass, right? So exergy, just like energy, can cross the boundary of a system, right? and exergy also can be stay in three different forms, so like which is heat, work and mass, right? So exergy transfer of a system definitely is recognized by the exergy is crossing the boundary of that thermodynamic system, right? So I mean we can determine either the exergy gain or exergy loss during a thermodynamic process, right? And only like basically two forms of exergy interaction, two forms of exergy interactions associated with a fixed mass system. And those are number one, heat, and second is work, right? So let's take a look on the exergy transfer due to the heat, right? So exergy transfer by heat, right? So basically exergy is nothing but the useful work, right? So from the thermal efficiency definition, I mean I'm just writing this, giving this example, thermal efficiency expression, we know that W output divided by Q in, right? So this is the expression. However, this W output, which is nothing but the useful work, right? Useful work, which is also exergy, right? Exergy. So now we can write this expression as 1 minus T naught divided by T, right? The efficiency expression, and the W useful, which is the exergy, right? Exergy due to the heat, right? And this is the Q in. So that means we can write the exergy due to the heat or reversible work or useful work due to the heat, which represented by X heat, equals to 1 minus T naught over T times Q in, right? So that's the expression of exergy due to the heat. Now let's take a look at the exergy transfer by work. So exergy transfer by work. What is the expression? So the exergy transfer by work, x work, w work, equals to, it can be two different form. Number one, w minus w surroundings and only w, right? So if you have the first case, if you have a boundary work, right, boundary work, and if you don't have the boundary work, right, not crossing the boundary, then it will be for any other case that doesn't have the boundary work, this statement will be applicable, right? Other form. So this is the expression for exergy transfer. Again, exergy is nothing but the useful work, right? So basically when it's become when you have like a boundary, just we described here, let me show you here, that it has an imaginary boundary, right? So that means that we have to subtract the work producing due to the stream minus work producing due to that boundary. So that's what is happening here. Exergy transfer by work. So basically work without the boundary minus work with the boundary, so then that will become the useful work, which is exergy. However, if we don't have any boundary, then the useful work will be directly used for exergy, which is equals to x work, right? So now we saw that exergy change due to the heat and exergy change due to the work will solve some problem based on this topic. Also, let's write one more topic, exergy transfer by mass, right? How it's possible. So if you have a system, right, for example, if you have a thermodynamic system that has some sort of constant flow is happening, or mass flow is coming, right? Mass flow is coming, and then some constant mass flow is outgoing as well. So when the mass is coming to this system, it's coming with certain enthalpy, certain entropy, and certain exergy. When it's crossing that system, it's leaving the system with another enthalpy, another entropy, and different exergy, right? So that means that when the flow stream is coming to the thermodynamic system, it's coming with state 1 and leaving at state 2. Then also the exergy is changing, or the exergy is transferring from state 1 to state 2. So what is that representation? So basically the exergy of a flow stream, we expressed it in psi. When the constant mass flow is coming, then we just multiply that mass with that psi, and then it will represent the exergy change or exergy transfer due to the mass. So this is the expression for exergy transfer due to the mass, right? So we talked about the exergy change due to the work, heat, and mass. So now let's talk about the one more topic, which is 8.6. Basically, we in entropy chapter we saw that entropy increasing principle. However, in exergy we'll see that exergy decreasing principle, right? Exergy decreasing principle, exergy decreasing principle, or exergy destruction, right? So if we have, let's consider a closed and isolated system, right? So that means no heat transfer, no heat, work, or mass transfer, right? Transfer. So isolated system, right? So that means that exergy change isolated system, we have to, or Exergy destroyed, right? How much it is, we have to determine that one. So if we do the energy balance for such a thermodynamic system that is isolated with the environment, that means there is no heat transfer, no work transfer, or no mass transfer, then the energy balance equation simply becomes E in minus E out equals to delta E of this system, right? So basically there is no incoming, no outgoing, right? So the total change of the energy of this system is equals to 0. So that means from E2 to E1, which is equals to 0. Now from entropy balance, so if it is a isolated system, then entropy balance is equals to S in minus S out, right, plus entropy generation. For every thermodynamic system we saw that entropy generated, right, and then change in entropy of that system. So nothing is incoming, nothing is outgoing, only the generation, right? So that generation is S2 minus S1, right? So now if we multiply this second expression, let me write it number 1, come on, number 1, and this is number 2, 2 times T. If we multiply number equation by T naught, the surrounding temperature of that isolated system, then the expression will become T naught of S gen equals to so basically we are multiplying, let me multiply first and then we'll write. So T naught of S gen equals to T naught of S2 minus S1, right? Now if we subtract this equation from number 3, equation from number 1, then the expression will become minus T naught S gen equals to E2 minus E1 minus T naught of S2 minus S1. So subtracting 3 from 1, right? We'll get this expression. So now in the entropy or the Exergy change of a closed system, we just derived this that expression in the last class, which is x2 minus x1 equals to E2 minus E1 plus P naught of V2 minus V1 minus T naught of S2 minus S1. However, it's a isolated system and it's a constant volume, right? There is nothing is changing, volume is not changing, so that means that B2 and B1 is the same, right? So this expression will become x2 minus, this will be x1, x2 minus x1, which is equals to E2 minus E1 T of S2 minus S1, right? So now let's now if we compare this equation with, let me write this one 4 and this one 5, right? So we have E2 minus E1 minus T minus for S, like if we compare the S equation 4 and 5, we can write this expression x2 minus x1, which is equals to minus T naught of S gen, right? So what we are learning from this expression, right? So this expression is telling us that if the S generation, if S entropy generation of that system is greater than or equals to 0, that means that this number, negative number, is going up, right? So negative number is going up means that the exergy is destroying or exergy is decreasing. Exergy is decreasing. And if this number is 0, then exergy, S generation is 0, right, for reversible process, then exergy change also becomes 0. That means we can write this statement, right? Exergy of a isolated system during a process always decrease, but for limiting case, exergy can be 0 or remain constant. Limiting case of a reversible process, exergy remains constant, right? So basically the expression exergy change of a isolated system is either 0, equals to 0, or less than or equals to 0, right? So either it could be decreasing or it could remain constant, but there is no that isolated system exergy will increase. So this is the decrease principle. This is the exergy decreasing principle. Okay, now what is the meaning of the exergy destruction? So from this above equation right here, we can see that exergy is either decreasing or remaining constant, right? So from this expression, this we can write the exergy destruction equals to T naught of S gen, right, which is always greater than or equals to 0. That means that exergy destroyed is a positive quantity for actual process and become for reversible process, right? So positive quantity for actual process, that means for actual process exergy always destroyed, or 0 for reversible process, right? So that's the exergy destruction. So if we write it in, this is very important just to in a glance. So exergy destroyed for a thermodynamic system can be 3 form. It is always, exergy destruction is always positive, right, or always exergy destruction will happen for irreversible process, or it will become constant or 0 for reversible process. However, exergy destruction less than 0, it is not possible, impossible, right? Meaning that there is always some exergy destruction. There is no way that a system doesn't have the exergy destruction. So that's all about the exergy decreasing principle. So we'll go ahead and do some math problem based on those principle, and we'll try to understand how the exergy of a system is changing, or basically the decreasing. Thanks for watching this video. We'll come back with another video.